Hello. So, thank you very much for coming to this talk. And first of all, I would like to apologize for my strange English from Spain. And we would like to talk about railroads, security railroads. And we call this talk Dark Territory for some reason that we will see in this talk. So let's go. We are Gabriela Garcia and David Melendez. This project is has been performed together with my co-speaker Gabriela Garcia, but for personal reasons, I'm here alone. So, but I would like to say that this is a project of two people. So, what about dark territory? We call dark territory in this topic. It refers to a section on railway track that is out of control of the Central Command and Control Office. So, I would like to remark that in most cases, not all railway network is directly connected to a command and control. So, at a given point, especially in remote areas, the train pass through the tracks, and command and control has no data about train position or status until the trains arrive to the next controlled station or with the staff. So, fun with trains. Did you see? We're going to start explaining what is a railway block. Well, the tracks have to be divided into blocks to prevent two trains to crash. So we have to control the train position in every section, and we divide the tracks into sections, and a section can only be occupied with one train at the same time. So we send a train on the track, and immediately the section is blocked. So no other train can enter in the same section. How we achieve that? By dividing the track into sections. Section can be one section between two stations, the big red line, or we can divide the track into more sections between stations. That is the case of the last picture. So how we could divide that track? We use light signals. Okay, so we control the track of occupation with signals along the track. When a train enters a section, a red light appears behind the train to prevent another train to enter the section. Okay, this is pretty straightforward, I think. So, along the train, with the train traveling across the track, the train leaves sections behind it, and the section is released. The last section is available to be occupied by another train. and we have to leave a security separation, or at least one section. So a classic method to track the trains is an axle counter. So we, with this device counts the number of axles that pass through the device. So you can count the number of cars of the train. So this device is installed at the beginning of the section and at the end of the section to make sure that the same train has left the section and no carriage is lost in the trip. So how blocks are blocked? How tracks are blocked? We have several methods. The classic one is a token block, as you see on the UK historical trains. So a token is catched by the train driver and delivered to the next station. It's very antique, it's very legacy, this method, and is discarded in modern railways for obvious reasons. And another legacy blocking system is a telephone block system that the station staff calls to the next station by telephone and warns the next station that a train is arriving to the next station. So the next method is the electronic one. So we have automatic flow control of the trains, like a computer network. This is in computing we call this traffic control or flow control. So we have several signals activated automatically. So in one track we have several sections or blocks that are managed automatically. So the signals turn red, yellow, and green as long as the train passes along the sections. So one train prevents the train behind to catch the first one. This is the case of the double track, a double track system, which one track is for one direction and the other track is for the reverse direction. And this is a bidirectional automatic blocking. Maybe the most typical application nowadays. So we can use both tracks in both directions. So if we need a track, we are able to send two trains with the same direction simultaneously. Okay. So this is what a command and control looks like. The command control tracks the position of every train, but maybe not. Maybe we have several cases that in remote areas that command and control is not installed on tracks. Okay, so we enter the topic that occupies us today. What about if a train driver doesn't see the correct signal? For example, a train driver thinks that he saw a green light, but indeed it's a yellow or red. What would happen? Bad things, right? Not good. Very bad. So, on 20th century, engineers was afraid about this situation. So they decided to create or invent several systems to prevent the train driver to misinterpret light signals all over the world with different technologies, different kind of applications. Every country implemented this kind of security, but their own ways or technology and methods. So there are several kind of systems around the world, but they have in common a lot of things. So as an Spaniard citizen, so we decide to investigate about the Spanish case, especially. So in Spain, we have the announcement of signals and automatic braking. We call ASFA. That means anuncio de señales y frenado automático in Spanish. So the ASFA is not ASFA, no, we call ASFA as this sounds. So in ASFA we have two main items. One item is placed on the train, near of the wheels, and the other device is placed on tracks. So this is basically an schematic of the system. We have a railway signal. That signal is connected to a box, a connection box, and that connection box is connected to the command control. So also this connection box is also connected to a device on track. We call it a beacon or balise. We will call it beacon in English. It's like it's a device to transmit, to tell the train this symbol, the current symbol of the railway signal, red, yellow, green, and so on. So in the part of the train, we have an antenna that catches the signal of the beacon, and a processor that catches that signal and is interpreted, and is sent to a console that train driver sees that kind of signal. The train driver has to acknowledge what the symbol of the right signal that the train driver sees. So if the train driver sees a red or yellow, in the console appears a light that the train driver has to acknowledge with a button. He has to press the button or the train stops. If the train driver presses the wrong button, the train stops, okay, for security reasons, and apply the brakes. So in the ASFA case, we have several levels of implementation. The analogic system was invented on 1960, 70, more than 50 years ago. So it's very legacy system, but it's very robust in the sense of safety. is very robust. It works very well. So we have several aspects. They call aspect on every signal we have. We have red, we have green, crossing, railroad crossing, another green, yellow, more yellow, yellow and green. And this is a speed limit, okay? And the most important one is L7, L8. That means a red signal, red light. L7 warns to the train driver that is coming a red signal. And L8 is not warning, is immediately stop, because the train driver didn't stop before the red signal, okay? L8 must not be passed, never. Okay, how the train knows which signal is one. So we have L1 and the frequency, okay? L2, L3, and so on. We have some frequencies here that represent each symbol, okay? So, as you see, we have 3 levels of ASFA, analogic, and digital. In digital, we have more frequencies to see more aspects, more meanings, okay, more symbols. Okay, so what the train driver sees. This is the console. So, and this is the buttons that the train driver has to push when an ASFA warning comes. Okay. So this is the console on the train driver desk. Okay. We enter that territory here. Okay. In Spain and all over the world, from time to time, there are some accidents that could be prevented installing this kind of systems, because some crashes are from a train driver error and human error that becomes for not seeing properly the signals. Okay. So, how the signal works internally. So we have a track device, a beacon, that is, it is a device that is an analog circuit, okay? We have a coil inside the black box. We have a coil, a big coil, connected to a capacitor, okay, in series. So we have an LC circuit, a passive LC circuit. So that circuit is resonant at the specific frequency of each symbol. For example, if I want to make that beacon means like green, we have to tune the circuit at 60 kilohertz frequency. Okay. So we have to make a circuit that respect that specifications. If we want to change the symbol from green to red and so on, relays are installed inside the beacon to change the capacitance of the circuit. So by changing the capacitance of the circuit, we change the working frequency of the circuit, and we change the symbol, okay? This is changed by command and control remotely. But if command and control, by any reason, cannot control the beacon rests in the default frequency that it's the most restrictive, for example, red, okay? Okay, how it works, like induction, okay? Like the induction kitchens, induction toothbrush chargers, RFID, like mobile wireless chargers, okay? We have two coils that one coil is transmitting power and the other coil is receiving the power. So we have a wireless system, a contactless system, powered by induction, but inductive coupling, okay? So, why we know how that kind of system works? Because all the specifications, all the formal specifications were published along the years by several people, authorities, technicians, and so on. So, for example, a very strange device was repaired by the local technician in Spain, and he published the device on internet in a very old blog, like 90s, without CCS or so on. So, thanks to that image, we can think how the insights are built inside the system. For example, this device is a beacon tester, okay? Used by a technician, by some maintenance technician, and for example, a technician wants to test a beacon, okay? He goes to that device, and he puts the device, okay, near to the beacon to test at what frequency is working the beacon, okay? So we have two coils. One coil is transmitting, and the other coil is receiving, okay? One coil transmits an 111 kilohertz, okay, of frequency, and next to it is another coil receiving that frequency. What happens when this device is placed near to a third device that is the beacon? The resonant frequency changes to the symbol of the beacon, okay? So that is how this device can see the symbol that is transmitting the beacon. So we know that there's no authentication of any kind of security or modern security between the track and the train. So as a hacker mind, what will happen if we think about possible attacks? Maybe we use a circuit with a coil and a capacitor to induce the frequency we want the train to pick up to emulate a beacon. Okay, so we fake a real beacon. So we will theoretically we could stop a train by simply building a red beacon, a L8 symbol beacon. Okay, there is no password here. The only password is to get the right frequency working with the beacon, okay? We need a beacon that resonates at the correct frequency. That's the only protection of the system. What the requirements are, we need the inductance of the coil and the capacitance of the capacitor, okay? There is no aspect. There is no information about that, but we can think about it as an engineers, like where we are able to build that device, okay? So we think as a whole system, okay? We have to think we have to build the entire system, not only the beacon, to make sure that the system works, okay? So we first build a frequency generator that transmit with a coil that frequency, okay? And another beacon, another coil that receives that frequency, okay? That is the first device, okay? The first one is this. Okay, this device transmits the train frequency, the base frequency, okay? And another device very similar to this receives that signal, okay? That's how the trains know that the system is working. No more, no less. What happens when that two coils pass throughout a beacon placed on the tracks? The beacon placed on the tracks is that circuit, the beacon circuit, that is this device. Okay, this device we made it with cardboard and copper wire. That's all. Indeed, maybe it's an Amazon box for some reason. Okay, but this is the device of the track. Okay, it's the same thing. We can fake a beacon, okay? In this case, it's L5, 7.7 kilohertz. That means yellow. Okay, but we have to make the two components. So we have a coil and a capacitor and a transmitter. Okay, we see with the vector analyzer. We know the frequency response, and we can tune the frequency that the working range of frequencies. Okay, that one is this one, and it's the receiver. The receiver is tuned to receive a little bit the power of the train and more the range of the frequencies of the track beacons, okay? And what if, so we have to make this device taking into account the impedance of the circuit. The impedance of the circuit, we have to achieve a circuit that is only resonant at a specific frequency. In order to transform the 111 kilohertz of the train to be converted by this device into another frequency that is red, yellow, green, and so on. So that is received again by the second coil of the train. Okay, we have to make like an electronic engineer an LC circuit, a coil and capacitor circuit that is resonant at a given frequency. We have to make the circuit resistive and that given frequency. more frequency, the circuit is inductive. It's not transmitting energy. The less frequency, circuit is capacitive. There's no transmitting of energy, okay? So we achieve the red signal here, place, and 95 kilohertz, okay? The impedance, the resonance, and the standing wave ratio is optimal just in the red frequency and the red symbol frequency. So that's the device. That's all. No more, no less. No batteries, no electronic, no nothing. Just a coil. Even it has no capacitor because we take advantage of parasitic capacitance of the circuit. So we save money, okay? Okay, so what the train sees when the trains go on the tracks, okay? This is a Fourier, this is a frequency analyzer. So we have 111 kilohertz always. Always. The train is transmitting and receiving, Okay, what happens when the trains pass along a beacon? Another peak appears momentarily and a given frequency that is the symbol red, yellow, green, and so on. So in this case, it will be yellow, I think. Yeah. When the setup, you think the track is here and the train passes. So that peak appears when all the setup is near each other. Okay. Even public documents tell you where to place exactly the device. There's no problem here. So another systems are the same, like the AWS in UK. In Japan, also the legacy control automatic train stop system has the same technology as we know. And the several systems in Europe, like Germany, like the Indusi, and so on. In North America, we have another system that displays on a side of the tracks. And the new one is the European train control system that is very similar to the modern ATP, the modern Japanese ATP. So we will talk about this in another talk because this topic is indeed interesting because we think we could do things like this, maybe, who knows? So security measures, we suggest periodically checking the beacons. And thank you all. Thank you, that people, to help to release this investigation. And thank you, all you, for attending this talk. Thank you very much.